This makes VLF wave hunting even more fun. You can customize the method to your latitude and longitude. With a touch of research instinct and this method, you can locate the source of that VLF signals. By the way, I'm using a homemade VLF loop antenna, which is great fun for wave hunting, as it's outperforming others in this range. Videos about its design and DIY suggestions are linked on the top right corner. Now let's dive into the world of VLF signals. On the web you can find lists of stations from around the world. But you are wondering if your receiver and your antenna are sensitive enough to receive certain stations in your location. And if so, what is their signal strength and direction? Here's a method allowing predictions based on distance, transmit power, day-night transition, antenna gain and frequency. We put this into an Excel tool that makes VLF wave hunting even more fun. You can add stations to the list and the forecasts for your location will be updated automatically. We will explain how it all works in a minute. Because I can't keep that from you. PCBWay has some great offers again. The cool purple solder mask is for free until end of October, and there are great discounts on TPU material. White PLA material for prototyping has been added. Simply fantastic offers for hobbyists and professionals. Take the easy way with PCBWay. The distance between 2 points on Earth, given by latitude and longitude, is calculated using the so-called Haver-Sign formula. Delta V and delta theta are the differences of the coordinates. The resulting quantity c times the Earth's radius essentially gives the distance traveled by the VLF radio waves. Alpha, also called azimuth, is the radio signal's horizontal angle of incidence, defined as north over east. It's calculated from the transmitter and receiver coordinates using this equation. For an optimal signal, you want to point your antenna in this direction. Consider Prec as the received level of a signal, transmitted with an effective isotropic radiated power, PTR EIRP. Along its way, the signal is reduced by a certain propagation loss. During daytime, reflecting layers in the ionosphere are lower than during nighttime, causing additional signal loss at transition. It's a typical telecoms engineering approach. The isotropic received power is calculated so that you can determine the signal strength based on the receive antenna gain. We are essentially just adding up dBs. VLF stations typically have low directivity and high efficiency. So we can assume that PTR EIRP is almost equal to the transmit power. A powerful transmitter typically has 1000 kilowatts corresponding to 90 dBm. The propagation loss is depending on the distance d, no surprise. A frequency-dependent term seems strange here, but the equation is correct. It's the consequence of our comms engineering approach. If the radiation were to propagate in free space, the propagation coefficient gamma prop would be exactly 2, since radiation intensity would decrease with squared distance. In reality, the VLF signal is losing energy to the ground and to the ionosphere. As these effects are complicated to calculate, I'm using a so-called heuristic model instead. In other words, it's an approximation tuned by measurements. Essentially, we're just using a larger gamma prop to account for the additional loss. The actual gamma prop setting is coming in a minute. Day-night transition loss is added, as well as the penetration loss in case you're operating the antenna indoors. Finally, we need to consider the receive antenna gain, which is determined by its effective area divided by the effective area of the isotropic antenna. Luckily, the effective area of a mug loop is equal to its geometric area, which you can easily measure in square meters. The effective area of the isotropic antenna is given by this equation. And that was the reason for the somewhat complicated approach. Now, let's take a look at what the tool actually can do. First, enter your geographical coordinates in decimal format. These are some examples for other locations. My VLF loop, sloppily attached with 3 nails, is spanning about 2.2 square meters. I'm estimating 10 dB penetration loss since I'm operating my antenna indoors, and the day-night transition loss shall be 12.5 dB. 3.2 is a good starting value for the propagation coefficient. The chart instantly displays the predictions for all stations whenever you change any inputs. Light blue is the prediction with day-night transition, dark blue is without. Next, I'm comparing a signal from a known station in 800 kilometers distance, which I am receiving on my RSP-DX SDR. Currently, there is no day-night transition between the station and my location. Now I'm tuning the propagation coefficient to match prediction and actual received signal strength. And that's it. The tool is now customized to my configuration and location. I'm getting realistic predictions for all stations in my list. This also works for any other location worldwide. When entering the coordinates of Concord, USA, instead of Stuttgart, Germany, all stations in Europe are predicted weaker, while the station in Cutler, USA is significantly stronger. Here are examples for comparison for Stuttgart, Concord, Sydney and Lisbon. Besides signal prediction, the list is containing additional information for wave hunting. There are the station's distances and the angles of incidence. Your receiving antenna's gain at the respective frequency is calculated here. The average signal strength is shown in white. Light blue represents signals with day-night transition, dark blue those without. You can now either compare forecasts with signals actually received to identify them. Or you can use predictions to turn your antenna to the right direction and search for specific stations. Please note that some of them are not permanently active. Links to interesting VLF websites and communities are provided below the video. Unlike shortwave, VLF doesn't depend that much on the ionosphere. Furthermore, influence of terrain and weather is low due to its huge wavelength. The simplified propagation model only works in the VLF range. If you are interested in the tool or predictions for your location, please let me know. Have fun hunting for radio waves. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.